Welcome to Friday. So today I want to go back and look at the previous ODPs that we've been doing because I generally like to go over those after they're turned in, and I've neglected to do that. So I want to just kind of review the last couple of ODPs, 202 and 3, to make sure people are up to speed on how those could be done, because that's part of your programming assignment. Then I want to talk about ODP 204, and then I want to make a quick comment on putty and some ideas for using putty more efficiently if you're using putty to get to the Linux server. And then I'm going to talk about inserts and deletes and linked lists. Okay, so any questions before we get going? Our front row has vanished. It's like prime seating available. So ODP 202, initializing the linked list, this was a version of the code that should work. So I declared my struct node up here, and I went ahead and did a typenef. I defined an uppercase node to be a struct node, so I can just say uppercase node star, for example. So the init function takes a pointer to a node, which means it's an array of these nodes, and then two pieces to this. One, initialize what we now call the sentinel, element 0, set the data to 42, next to -1, mark it as valid. And then a loop to set the other nodes to the odd values that were specified, where data is 999, next is that, and valid is 0. In the for loop, right, it begins with I equal to 1, and it says, well, I is less than or equal to 99. So if you declare an array with 100 elements, first element is 0, last element has index 99. Right? If you have an array with n elements, last element has index n minus 1, because we always start from 0. So either less than or equal to 99 or less than 100. Either one of those gets you there. So that's a working version of init. And then get node. So again, the usual struct node, and then it takes an array of struct nodes and one for loop. Basically start from index 0, and here I'm looping while we're less than 100, and just check the valid flag on index element I, and if it's equal to 0, return I. That's the location of the first invalid node. If you come all the way through this loop and you never returned, it means that all 100 entries had a valid flag that was not 0, so that's where we say return -1. Question that came up in the earlier section was why the order of these declarations in the struct node matters. Data, next, valid. Why does it have to be in that order? Any ideas? Because if I write this function and I do next data valid and I try to assess, I won't get 10 out of 10.
Because in your main function where you define structure, it's in that order in C statement?
Yes, so in my main function that you're linking with, I'm using this order for a struct node. And if you put it in a different order, things will fail. But what does it mean because C is picky? In what sense is it picky? So there's a little bit of 270 in here.
Can you just see it as a different type of structure?
Sort of. How do structures work in C? When you compile and you turn it into assembly, and then you assemble that and you turn it into ones and zeros, and the CPU is just getting a bunch of binary.
It's a series of addresses.
It's a series of addresses, right? When I say check the valid field, the word valid doesn't get coded into the machine code.
It's the address of where valid starts.
Exactly, it's the address of where valid starts. So in this case, we've got data, next, and valid. So if we say something like struct node n. N will refer to this first field. It's an integer, so it takes 4 bytes. If the system wants to do something with the next field, it's going to take the address of n and it's going to add 4 to it. And that's where it's going to look for the next field. And if it wants to look at the valid field, it's going to take the address of n, it's going to add 8 to it. And that's where it's going to look for the valid field. And you don't have to take my word for it, because we can use GDB. So I don't know if I have an example.
That's weird that there's a weird.
It is weird that there's a weird. So here's a main program that that I was using to test ODB 203. So let's just compile this with debugging. And let's hop into the debugger. Let's compile it with debugging this time. So I have this thing called D. It's an array of struct nodes. So if I print D, I get this big long list of each element of D, and it's got a data piece, a next piece, and a valid piece. So if I print D bracket 0, that's a struct node. Data is that, next is that, valid is that. If I print the address of D bracket 0, I get this big long number, 7FF, and so on, ending with E090. So this is the location of D bracket 0. If I print the address of D bracket 0's data field, I get the same thing. So now I'm starting to make a memory map corresponding to the structure. This is D bracket 0 dot data. And if I print the address of the next field, that's E094. And if I print the address of the valid field, where do you think that might end up?
E098.
E098, excellent. So by the time we get everything compiled and linked and we're running an executable, this is what the data structure looks like to the CPU. If it wants to access the valid field, it's going to take the address where D0 began and it's going to add 8 to it. Now in my main program, if I had a different orientation to these, and I had the data piece down here and the valid piece up here, when my main program is using the valid piece, it's going to take the address of D0 and it's going to add 4. And it's going to be talking about a different location in memory. So these things get confused with one another because nothing about the names of these fields is stored when you compile your program. It's just offsets from the beginning of the structure. So they've got to line up. Now in your main program, you could put these in a different order, and in your function, you could put them in that same different order. Everything will work fine. But as soon as you try to link to somebody else's program, you've got to make sure your structure is in the same order. And since you're linking to my test bed, you've got to use the order that I used in my code. So that's where that makes a difference. Where do you think d bracket 1 dot data is going to be stored?
102. E102.
Yeah, it'll be in hex, but location 12. So E09C. All right, so that's d bracket 1. And d bracket 1 dot next is going to be E0A0, right? And these are just counting by 4 in hex. So in general, d bracket I, well, we don't have to do this, but the compiler does. It's going to be stored at E090 plus, and we're taking 12 bytes for each element of our array. So I'll go ahead and use evil decimal, 12 decimal times I. And d bracket I dot next is E090 plus 12 decimal times I plus 4, and so on. And this is all the stuff that the compiler puts in its brain and ponders while it's compiling your program. And in your code, when you say d bracket I dot next, it replaces it with the address where d bracket 0 starts, plus 12 times your index variable, plus an offset of 4. And we touch on this really briefly sometimes in 270 when we're talking about those indirect file registers. This is what you would use those indirect registers for. You put a base register that corresponds to the beginning of your structure, and then you just calculate an offset. All right, so ODP 204. So 204, we're starting to move into this array of struct nodes as if it was actually a linked list. And the idea of 204 is your array is storing a list. So let me draw our picture again. And we've got 3 fields, data, next, and valid. And we know that element 0 is our sentinel. And the purpose of the sentinel is to point to the first data node. Okay, what your function should be doing is returning the data value of the first data node in your linked list. So for example, suppose your list looks like this. Here's your sentinel. And it points to a 17, and that points to something else, and so on. You want your function to return 17. And your function takes 2 arguments. The first is the linked list itself, so the array of struct nodes. The second one is a pointer to an integer that I'm calling error. And it's a pointer to an integer so that you can set a value to that variable. Now, if you look at your list and there is a data node, you set error to 0, and you return the data value of that first node. So in that case, we'd set error to 0, we'd return 17. If the list is empty, set error to 1 and return a 0. So that's what all of this wordage boils down to. Right? Take the LL array, assume it's a linked list, element 0 is the sentinel node. If it points to a data node, set error to 0, return the data value. Otherwise, set error to 1 and return a 0. So how do we do that? Look at the next field of element 0 of the array. If it's equal to my null, right, -1, then set error equal to 1. And error is a pointer to an integer, so this says take the thing pointed to by error, set that to 1, and return a 0. If this is not equal to -1, let's say this is equal to 4, then look at element 4, find the data value. Set error equal to 0, and return whatever this data value is. So linked list bracket 0 dot next close bracket dot data, or something like that. But you can do it in pieces. Right, so find what this is, go to that entry in the array, grab the data piece, that's what you want to return. And logically what you're doing is giving the user back the data value from the first node. If there's no node, we're returning a 0, but we don't know if that means that the data value is a 0 or there was no node. Right, we could have a list where this was a 0, in which case our function would also return a 0. Or we could have a case where there was no data stored anywhere, in which case the function would also return a 0. So the error variable lets us differentiate those cases. So if error is 1, we know the list was empty. If error is 0, the list was not empty, and the return value is actually the first node's data value. Does that make sense? All right. So the rest of it is the usual drill, right? Testbed is main 204. Compile it in the usual way. Test it with the assess command. If it's not working, write a main program and test the function yourself. Right? Use your assignment statements to create an empty list. Call your function, make sure it sets error and returns 0. And then have this point to something with a data value, make sure it sets error to 0 and returns the correct data value. And if it's not, go inside GDB. Okay, we're going to start using GDB more and more. And this thing that we were just doing, where we were making this memory map, we're going to start doing this a lot, especially in PA2. PA1, we've got everything in an array. We can just kind of go into GDB and say print the array. But when we're storing these things somewhere other than an array, when they're just locations in memory, we're going to want to start using GDB to figure out where things are stored and then making pictures with addresses on paper so we can understand how this structure is set up in memory. So keep using GDB, get more and more comfortable with it. Okay, it's going to be your best friend throughout this course. And it's going to be your best friend in your 3rd and 4th years of all of this. All right, so any questions on 204? So that's due tomorrow morning. I will not post new ODPs on the weekend. Well, I might post them, but I'm not going to ask you to work on ODPs over the weekend. Okay, so I won't post one, Saturday morning or Sunday morning. So don't worry about that. But I'll probably post one Monday morning, which will be due Tuesday. Okay, but this is the last one for a while. All right, let me make some quick comments on putty. So how many people here are using Windows and are using putty to get to the server? All right, so when you run putty, it brings up a window like this, right? So some things you can do. You can go ahead and type in your username on the server at linux.engrcs.com. Right, so and I know it's really tiny up here. I don't have a quick way to make it bigger. But I'm typing in nick at linux.engrcs.com, which is my usual login. And over here under window, I'm going to say how many columns and rows I want, so it's normally 80 by 25, but you could make it bigger if you wanted. Lines of scroll back. This is how much memory putty has when you go back and you try to see what you did earlier, and normally it's like 2,000 or something really small. So I've got mine set to about 1,000,000 right now. Right? That's enough for at least a few hours worth of coding. And you're doing something and something doesn't work and you make some changes and you go back to how you had it before and suddenly it starts working and you're not sure what happened, right? You can scroll back through and see like the whole history of your session. There's been times when I've accidentally deleted code and I didn't have a backup and I wasn't using Git, but I could scroll back and there was a spot where I had looked at my code and I can copy that and paste it into a file and get back most of my code that way, right? It's always helpful to have the ability to go back and see what you've done. The first time I ever like hacked into a system I wasn't supposed to, this was how I was able to do it, because I had done something and nobody had any idea what I had done, but I was able to go back and see, and we were able to piece it together. So it's good for all kinds of things.
That's kind of interesting.
And that was only hacking for knowledge, not for like doing bad things.
What were you?
Oh, that's another story. So, and this goes away once you close out putty. Okay, it won't remember your history from before, but if your putty session window is still open, you can go back and see what you've done, and if you kind of keep it open, you know, you can go back a few days and sometimes get back information. So, so you can set your lines of scroll back. Appearance, right? So I like bright text on a dark background, so you can come under colors and set your foreground color and your background color. Appearance, you can change your font. So any mono-spaced font will work well. Proportional spaced fonts don't work well with coding because things don't line up. But Courier New, Free Mono is the one I have. In this case, those all work well for coding. And you can set your font size. So I like a bigger font. Right, I have a 1920 by 1080 display, so if I use 10-point font, it's really small for my eyes. So I use a font size of 16. So you can set all this up, and once you've got it set up, go back to Sessions, and under Save Sessions, type in Default Settings, and say Save. Or you can make a new session, so I can just call this Nick, and I can save it under that. Okay, so now next time you come into putty, all you got to do is hit an Enter key. And it brings up your session and your colors and everything else is set, and all you got to do is put in your password. And you're good to go. And I got 1,000,000 lines of scroll back, or the beginning of the session, and so on and so forth. And this is a general strategy, right? Particularly in a Linux environment, you can customize almost everything. If there's something that you always do every time that something's going on, every time that you want to work on your program, you have to log in and you have to do this thing and you have to go into this directory and do this other stuff and so on. Throw it all in a script, right? Or make yourself an alias, or put it in your bash RC if you want it done absolutely every time you log in. And if there's a script that you always want to run, make an alias for it. Call it Go. And when you say Go, it executes the script. You can set up the environment how you like and put it in a way that, you know, works whatever is going to work best for you, basically. There's a gazillion editors. If you don't like VI, find an editor you like and set that up. Set up VI to be an alias to that editor that you prefer. So now you can still keep saying VI because you got the habit of that, but it brings up Pico or Tico or Emacs or whatever you like. If you're using Emacs, you probably already do that. All right, so I just wanted to mention that because I never got around to showing that in 224. But that's available. All right, so let's write some pseudocode for linked lists. And I'm going to stick with pictures here, but you can translate this into code, you know, knowing that your picture is mapped to an array of struct nodes. So we have a header which refers to our sentinel. and our sentinel points to our first data node, points to our second, points to our third, and let's say this is the end of the list. If we're implementing this with an array of struct nodes, header is just an integer and it's equal to 0, and it never changes. And it tells us our sentinel is stored at index 0 in our array. So let's look at the delete function. And let's say we want to delete the node containing 20. So our general approach, remember, is going to be start at the beginning, look at the first data node, see if we should delete that. If not, go on to the second node, see if we should delete that. Keep moving through the list, right? Each node has a pointer that tells us where the next node is, until we get to a node that matches the number we're trying to delete. So this node's data value is equal to n. This is the node we want to delete. The one slight trick is that once we know this is the node we want to delete, we also need to know what the node is right before it. So as we're moving through the list, we need to keep track of the previous node as well as the current node.
A before and after.
A before and after. Or in this case, I'm going to call it previous and current. So I'm going to start off with previous equal to the sentinel and current equal to the thing the sentinel points to, because I don't want to delete the sentinel node, right? This is the first node I might want to delete. I don't care about the data value in the sentinel. So I'm going to start current off at the first data node, previous is the sentinel, and I'm going to say is the data value of the current node equal to n. So let's write some code. So previous will be the header node, which is just 0. Current will be whatever the previous node's next field was. So right now, this code basically makes previous point to the sentinel, current is the first data node. And now we want to know, is current the node we want to delete? So if current data equals n, delete current. And this is pseudocode, so I got a single equals instead of 2. So if the current node's data value is equal to n, delete the current node. And we'll write the code for that in a little bit. Otherwise, what do we want to do? Move down the list one spot. We want to change current to be the next node, and we want previous to be the current node. So we can do that a few different ways. Let's move down list. So I'm going to say previous equals current, and current equals current.next. I could also say previous equals previous.next, current equals current.next. There's a lot of ways to do this. So this will change previous to here and current to here. And then we're going to go back up to the top of our loop. So this was initialization. This is where our loop begins. So throw all this in some kind of while loop. Well, now we're going to check current's data, which is 20, and see if that's equal to n, and I'm supposing we're trying to delete 20. So this if statement is going to fire. So how do we delete this node from the list? What do we have to do to the picture to remove that 20?
Just have the previous arrow go around it.
Just have the previous arrow go around it. So take this previous arrow and put it over there. Okay, how do we write that in code?
Set previous.next equal to current.next.
Cool. Is that what you were going to say?
Yeah.
Okay. So previous.next, that's the arrow. Set it to whatever current.next is, whatever current was pointing to. Now your previous node points where the 20 was pointing, which means it basically skips over the 20. So the 20 is removed from the list. Free the memory. Since we're using memory somewhere, we were using memory somewhere to store this 20, and now this 20 is no longer part of the list, we'd like to release that memory so that it's available to be used in the future. This is what this release node function in PA1 does. It basically finds where this was stored in the array, and it sets the valid flag to 0. And when valid is 0, it means this location in the array is unused. And your get node function might return that location, so we can reuse that storage location. And then we just return. And there's a whole delete routine, almost. So what can go wrong with this?
What does it do if it loops through all of this?
What does it do if it loops through all of these? So suppose we tried to delete, 50, and 50 was not in here. So this would become previous, and this would become current. And 30 is not the thing we're trying to delete, so this would become previous. And current
The current is a null.
is going to be a null. And if we come back here and we say, well, is null's data equal to n? That doesn't even make sense. So it will do something weird in PA1, and PA2 it'll just be a good old seg fault.
So
Well-
there needs to be an if statement before that, checking
Yes.
for null.
So we need to check to see if current is null. So we could code this whole thing as a while loop that said, while current is not null. And then if we kick out of the while loop, we know you're trying to delete something that's not in the list. But if you're lazy like me, there's an even easier way to deal with this, which is before you do any of this, call your search function. See if n is in your list. And if it's not, don't even bother with the rest of this. And if it is, you're guaranteed that eventually it's going to find it. So you can do it either way. Okay, but that's the gist of a delete function. And again, the point, the lesson I want you to take from this is not the code, right, the pseudocode. It's the way that we decided what to write here based on what we were doing up there. Right, so how do we move through this list? How do we know when we're at the node we want to delete? What do we adjust to perform that deletion? And the answers to each of those questions translates into a set of code. Okay, that's the process that you want to get from this. Right, this idea of looking at the data structure, seeing how you're going to traverse it, how you're going to manipulate it, and writing code that corresponds to that. That's the magic. That's the piece that you want to get out of this. The code itself, worthless. Maybe you can translate it in and you can write your delete function, but long term, this by itself isn't really valuable. It's that process of analyzing the structure, writing code that corresponds to what you want to do. Once you've got that, you can tackle any data structure that you can imagine. And you won't need someone to tell you how to make a linked list of trees where each node in the tree is a doubly linked list with a circular head, right? Because if you know those pieces and you know how to do this, you can write the code. You got a question?
Yeah.
Yeah.
I was just curious. We don't really have to delete the data value of the node that we're deleting, do we? We can just leave it, and then next time we'll just replace it.
It's a really interesting question. If we delete this 20 node, do we have to do something with the data value? Technically, no, because when this node gets reused, our code will assign the data value. But it's an interesting question security-wise. Suppose you're storing a linked list of credit card numbers, and you're processing them and deleting them from the list. Do we want to leave that credit card number sitting in memory somewhere?
No.
Because somebody else might come along from a different process and use that same chunk of memory, and hey, it might have somebody's credit card number in it,
Or a few dozen numbers.
or a few dozen numbers. And you might think, well, but it's just going to be, numbers among everything else. How would you even know it's a credit card number? Oh, you can tell. If you know the code that's running on the system, and there's very little code in the world that's secret, right? Code, we assume, code algorithms, all that stuff is well known. Because you can look at the memory of the computer, you can reverse engineer it, you can reverse compile it, and so on. If you know how that's running, and it's very easy to take a 16-digit number and tell if it's a valid Visa number or a valid MasterCard number, because there's check digits in there. If you've done 215, we talked about check digits. You can do the same thing with credit card numbers, or social security numbers, and so on. So information can be gleaned from less to more. So we may actually want to do something like we're going to write a 0 when we release a node. Some systems do that. Some systems don't care. They leave it up to the user. All right, any other questions on deletes? Let's do insert. So let's insert a 25 into this list. And we'll write code for inserting n in general. And if we're trying to keep this list sorted from smallest to largest, as we're moving through the list, if the current node's data is smaller than the number we're inserting, we should insert somewhere after that current node. So 10 is smaller than 25, we're going to insert somewhere after 10. 20 is smaller than 25, we're going to insert somewhere after 20. When we get to 30, 30 is bigger than 25, and it's the first node that's bigger, we should insert right before that node. And so here again, we need to know what the previous node was. So this is what I called before after yesterday. I'll call it previous current again today. So we'll start off with previous being the sentinel and current being the first node. And we'll do our usual marching through. So previous equals header, and current equals previous dot next. And then we want to say if current dot data is bigger than n, insert before current. Otherwise, move down the list. So previous equals current, current equals current dot next, same thing we did before. And loop back up. So this is initializing previous and current. This down here at the bottom of the loop is saying let's move down the list one spot, set previous here, set current to the next node. Set previous here, set current to the next node. And this if statement fires when we're at a point where we want to insert before the current node. Okay, so how do we do the insert? Make a temporary node. So here's temp. set its data equal to n. So for us, that's 25. And then what do we do to the picture of the list to store this in the right spot inside the linked list? So let me update our pointers here. This is previous, and this is current, and this is temp. So physically on the picture, how do we squeeze temp in between previous and current?
We rewrite the address of previous to temp.
Right.
And the address of temp. And the next address of temp to current.
Exactly. So we want to take the next address of previous, and we want to point that to temp. And that's just previous dot next equals temp. And then we want to take temp's next and point that to current. And that's just temp dot next equals current. And then we can return. And are you seeing how the code is almost writing itself?
Yes.
Right? Previous next should point to temp. Well, you write a line of code or 2 lines of code that do that. And temp next should point to current. And if you do this as you're modifying the list, you write code, it will help you catch things like when you do things in the wrong order. Because sometimes the order in which you do these updates matters. And we'll see that with some other data structures. All right, so this will almost completely be our insert function. There's one case that we haven't handled yet.
Does it exist?
Same idea, but we're inserting, right?
You want to make sure that it doesn't already exist.
Oh, okay, so that's another situation, but we can do that with a search up front. There's still one more case.
What if you're replacing the last one?
What if you're putting something onto the end of the list? So as we're going through this loop, let's say we're inserting a 50. And let's forget about this temp node. Let's go back to our original 10, 20, 30. So previous and current's data is 30. That's not bigger than 50. So we're going to move down the list. So previous will be current, and current will be whatever current next is,
And it's null.
which is null. Just like when we were deleting, current is now null, and if I say current.data, that's meaningless.
You need if set even to check that changes null to whatever you're pointing to, and the new temp to null.
Right, so we can couch that inside a while statement. And we can basically say while current is not equal to null. And then do all of this inside that while loop. So once we make our adjustment to current down here to point to the following node, top of our while loop, if that following node is null, we know that we're at the end of the list. And so we come down here out of the loop, and our comment is add new node. Well, where should we add it in terms of our variables? The last node in the list is previous. So we can add our new node after previous. And so how do we do that? Temp equals new node. Temp.data equals n. Previous next should point to our new node. So let me make our temp node. We store a 50 there. So previous next should point to temp. And temp next should be null. we can return. And temp equals new node, temp equals new node, temp.data equals n, temp.data equals n, previous.next equals temp, previous.next equals temp. Temp.next equals current, well here we said temp.next equals null, but current is also equal to null. So we could have said temp.next equals current, and then return. This is exactly the same code as this, which should make you feel good. So we have to notice that we're at the edge, but we're still doing the same thing that we did when we were inside the list. So it's almost not an edge case.
It's only the edge case when we don't have it inside and out.
Right. Okay, well there's one other potential edge case, which is an empty list. So an empty list, we have a sentinel and its next field is null. So our initialization is going to say previous equals header, so this is going to be previous, and current equals previous.next, so current is going to be null. And remember, we put in a while loop which basically said, well, current is not null. Well, the first time we evaluate the condition of the while loop, while current is not null, current is null, so we're going to kick out of that while loop first time. We're never going to execute it. We're going to come straight down here. So this is inserting into an empty list. Let's see what the code does. It says temp equals a new node. Set the data equal to n. Set the next piece, set the previous next equal to temp. Well, previous is the sentinel, so we change that next to point to temp. And then set temp.next equal to null. And return, and that's a perfectly good looking list containing a single node with the value in.
What's the edge case then?
There is no edge case. Because it's not really an edge, because we're not inserting at the beginning of the actual linked list. We're inserting after the sentinel node. And that's what the sentinel node is doing for us. It's eliminating that edge case where you have an empty list. All right, so you have all the pieces you need to do PA1 at this point. That doesn't mean it's easy. Okay, I'm not brushing it away like now it's done, right? But you've seen all the pieces, and we've worked through the kinds of manipulations of the data structure itself. You need to translate this into the right kind of C code to deal with the fact that these things are stored as elements in an array of struct nodes. But you've got all the pieces now. So you should definitely be working on PA1 at this point. In one of the ways that we've talked about. All right, so have a good weekend. We will we'll talk about something different on Monday. We'll start moving towards memory manipulation.